Hey everyone, so we still see the same problem with the computer in the class, so I'm just going to continue from my laptop. So as you've seen, Canvas, again, all the details have been posted for Friday's exam. It will be during the class hours in this room, and it's an open book / open notes / open digital device exam. So you can take help from any of the previous examples that have been shown in the class, or you can take help from the book and so on. So, but most probably all the questions will be related to whatever we have discussed in the class. So it will be related to voltage and current divisions. It will be related to ideal op amps, non-ideal op amps, and frequency response of op amps. So in today's lecture, it will be an exam review sort of. So we'll look into different problems. We'll specifically look into the solutions of homework 2 and problems which are very similar to homework 3. So we'll take a look at those examples, but you can expect similar problems to come during the exam as well. There will be 4 questions in total, 25 marks each. But the questions will be, let's say, the answer should be, the solution should be smaller than what you have for the homeworks. Okay, please don't forget your calculators, because you might need to calculate certain things whenever you are trying to calculate for, let's say, voltage divisions or current divisions. It's good to have access to a calculator. So please bring your calculators with you. And I know that all of you have been studying hard for this exam. You'll do well. Don't worry about it. Good luck. Okay, so with that, today we'll discuss homework 2 solutions, as well as some of the problems which are very similar to your homework 3. All right. So the homework 2 problems solutions had already been posted in Canvas. So for example, all of these circuits that you see for homework 2, you are required to find out what is A infinity. And A infinity is basically the gain of the circuit or gain of the system, the whole system that you see, not just the op amp. Gain of the whole system, assuming that the op amp is ideal. So assuming that the op amp has an infinite input impedance, the op amp has a 0 output impedance, and the op amp has an infinite gain. What is the gain of the system? That's what you're required to find out for A infinity. Okay, and infinity just means that the op amp has infinite gain, but the system does not, because the system can have certain kinds of feedback, and because of the feedback, the gain of the overall system will be less than the gain of open loop gain of the op amp. This is something you have learned when you were studying frequency response as well, right? That because of the feedback, the gain of the system reduces by T0 times. In fact, if you go do the math, it will reduce by 1 plus T0 times. So again, just going a little bit into theory. Remember the formula for negative feedback? It's A divided by 1 plus A beta, where A is your open loop feed forward gain. That's basically the gain of your op amp. Beta is the feedback path gain. So, and again, you know that A times beta is basically your T0. So A times beta is basically the overall loop gain, which is T0. Okay. So what is happening to your open loop gain of the op amp? It's getting divided by almost T0 times, assuming that T0 is very high. Now you had a question yesterday that what if T0 is equal to 1? Right? That your beta is equal to 1 upon A. Right? That's the question you had. So in that case, a lot of the assumptions that we will make will not remain true. What will not remain true? That we assume that this T0 is very high, or A times beta is still very high, even though beta is less than 1. But because A itself was, let's say, very high, 500,000 or 10,000. So the value of A was very high. A times beta still remained very high. So 1 plus A times beta, that we approximated as T0. So that's why we said that the open loop gain will reduce by a factor of T0. Similarly, open loop bandwidth will increase by a factor of T0 when you put things into closed loop. So the meaning of open loop is that there's no feedback. That's it. The meaning of closed loop is that there is a feedback. That's the difference between open loop and closed loop. That's the only difference between open loop and closed loop. That either you have a feedback or you don't have a feedback. Now, if you have a feedback, your gain reduces by T0 times, assuming T0 is very high, much higher than 1. If it is not much higher than 1, then it's basically 1 plus T0 times. So your gain reduces by 1 plus T0 times. Similarly, your bandwidth increases by 1 plus T0 times. If you follow the math strictly. But generally, we'll assume that A times beta or the factor T naught is much, much higher than 1. So loosely we say that the gain will reduce by T naught times and the bandwidth will increase by T naught times. And that's generally true. If your T naught is, let's say, 50 or 100, it doesn't matter whether it reduces by 100 times or 101 times. Right? It's almost practically it's the same. Yeah. So just keep that in mind. And in the exam, you can either say that, okay, my gain is reducing by 1 plus T naught times, or it is reducing by T naught times. That's basically the same, and it will carry the same weightage in terms of grading. Similarly, when you talk about frequency or the bandwidth, the open loop bandwidth will increase by, strictly speaking, 1 plus T naught times, and loosely speaking, T naught times. Okay. And that just comes from the formula. So, but because T naught is generally much, much higher than 1, you can say that 1 plus T naught is almost equal to T naught. Okay. But if that's not true, Alejandro, you posted that question yesterday, right? That if beta is equal to 1 upon T naught, then A times beta or your loop gain is equal to 1. That's a very special case. You do not generally see that in actual circuits. But if that happens, you cannot assume that 1 plus T naught is almost equal to T naught, because then 1 plus T naught will be equal to 2, whereas T naught is equal to 1. But that's a very specific scenario. So you don't generally expect that in any circuits. Okay. So the other things you wanted to find out was R in, R out. And for R in and R out, again, I hope all of you get how to find out R in and R out. It's basically you put a test voltage source or current source at the input side or output side. And before that, you should kill all the independent voltage or current sources. So short all the independent voltage sources, open all the independent current sources. It's same as what you used to do for Thevenin equivalent circuit in your circuits 1 class. So kill all the independent voltage and current sources, and then put a test voltage source or a test current source at the input side when you're trying to find out R in, or put a test voltage or current source at the output side when you're trying to find out R out. Look at the voltage over current ratio in that test voltage source or current source, and that gives you the resistance. Now, there might be a question that at what point do I insert that test voltage source or current source? So for example, let's say first problem, if you want to find out, if you are trying to find out R in at this point, so which means that at this point, you're trying to look towards the right-hand side, and you're trying to find out what is the input resistance. So what you'll do is that you will not even consider what is connected on the left-hand side, because you are asked to find out the resistance looking into the right-hand side. The left-hand side does not matter at all. There could be hundreds of things connected on the left-hand side, and still it doesn't matter. Because what you're interested in is to find out the resistance looking into the right-hand side. If I look towards right, I don't know what's there in my left, right? It's the same concept, just in terms of circuits. Okay, now at this point, at the point where the R in is indicated, at this point, you will connect your voltage source, test voltage source, let's say Vx. You'll try to find out how much current goes in or how much current goes out of that voltage source. Let's say that current is Ix. The ratio of Vx over Ix will be your input resistance. Same thing applies for the output side, that you want to find out the output resistance at this point, looking towards left. So looking into the circuitry on the left-hand side, you try to find out what would be the test voltage to test current ratio, and that would be your output resistance. And then, of course, the loop gain for each circuit, which I think all of you already have gotten a hold of, that how to find out the feedback factor beta, and the loop gain will be A times beta. Okay, now if you look into the solutions, first of all, the A infinity for the first case is basically V naught over Vs, the output that you're seeing over here on the right-hand side, divided by the input voltage or the source voltage, which is denoted as Vs. Because this is an ideal op-amp for part A, your input resistance is infinite, your output resistance is 0, and the op-amp itself has infinite gain. So you can use your nodal equations and find out what would be your V naught over Vs. Okay. And for that, just assume that there is no current going into the op-amp because the op-amp has infinite input impedance. So whatever current comes out of, let's say, Vs, and whatever current goes through R1, the entire current will also go through R2. Again, just the nodal analysis, nothing new. So this is not even part of this class or this course, that you have already learned about nodal analysis in your circuits 1. So I would hope that you would know KCL, KVL, and how to apply KCL and KVL. So whatever current goes to R1, that same current goes to R2 as well. Why? Because at this point, the current should have been divided into two parts, but it will not, because the current that can go in the op-amp is equal to 0. So no current will go inside the op-amp. All the current will flow through the R2 branch. And if you assume that, then you can write down the current through R1 as Vs over R1. The current through R2 will be equal to minus V0 over R2. That's just, again, following the nodal analysis and also applying the virtual ground property. So whenever this op-amp is in feedback, you can assume that the difference in AC voltages at the two terminals is 0. So effectively, the difference of the AC voltages in the two terminals is equal to 0. So that's why the voltage at the positive terminal, the AC voltage at the positive terminal will be equal to the AC voltage at the negative terminal. Now, what is the AC voltage at the positive terminal? Because you have a resistance R3 connected to ground, and remember that no current can go into the positive terminal, right? So there cannot be any current going into the positive terminal, which means that the voltage across R3 is 0. So the bottom terminal of the R3 resistance is 0. The top terminal of the R3 resistance is also 0. Because there cannot be any current flow. If there is no current flow, there is no voltage difference. So the positive terminal of the op-amp is at 0 voltage, which means due to the virtual ground property, the negative terminal of the op-amp will also be at the 0 voltage. Now you can apply your KVL very easily, that you know that across the R1 resistance, the left-hand side is Vs, the right-hand side is 0. Across the R2 resistance, the left-hand side is 0, the right-hand side is V0. So you can just write your KVL equations, and from there you can find out what is A infinity, which is basically V0 over Vs, and that will be equal to minus 4 volts over volt in this case. Questions? No, it's just that you understand that the R3 will not have any significance, right? Because it's better you know that now rather than later on in the future or during a job interview, right? So now, because you have solved this homework problem, you know that R3 will not have any significance. So if this question comes in a job interview, you should be able to do it in a second, right? Otherwise, you might get confused that, okay, what's the job of the R3? So there's the R3 does not have any effect in this particular case. Okay, Rin, what's the input resistance? Again, you kill all the independent sources, you put a test voltage source at the input side. You do not have to look into the left-hand side because you're trying to look into this point, looking towards right, and try to find out what is the test voltage to test current ratio. Again, the same things that we have learned in class. And now, because the right-hand side of the R1 resistance is at 0 potential, AC 0, right? AC ground. That's something we have established already, that the right-hand side of the R1 resistance is at AC ground because of the virtual ground property and because of the fact that no current can go into the op-amp. So if that is true, the left-hand side of R1 resistance is at is connected to the test voltage. The right-hand side is 0. So what will be the test current flowing through the R1 resistance? It would be the test voltage divided by the value of the R1 resistance, right? So that's why Rin is your Vs divided by the current that flows through the R1 resistance. And which means that the Rin, the input resistance, will be equal to R1. So input resistance is equal to R1. What happens with the output resistance? Again, we have discussed this multiple times in the class, that looking into the op-amp, you'll see a voltage source. The output of the op-amp is basically a dependent voltage source. So as you are looking into the op-amp from the output side, as you are looking towards left into the op-amp from the output side, you see an ideal voltage source in this case, because we said the op-amp is ideal. So what's the resistance of an ideal voltage source? 0. So in this path, you'll see a 0 resistance, and there is a parallel path which has some resistance, maybe R2, R1, and many other things can be connected into that path. But if you have a 0 resistance connected in parallel with some other resistance, a finite resistance, what is the equivalent resistance? 0, right? 0 in parallel with any other value will be equal to 0 in terms of resistances. Correct? And that you can just write down the formula for parallel resistances, right? So what's the formula for parallel resistance? It is What is the markers here? So two resistances R1 and R2. The parallel equivalent of this, looking from let's say this side or even that side, is R1 times R2 divided by R1 plus R2. And now we are saying one of them is equal to 0, so the numerator becomes 0, the overall resistance becomes 0. Doesn't matter whatever the value of the other resistance is. So as you are looking into the op amp, you see a 0 resistance. So whatever is connected in parallel to it does not matter. The overall resistance you'll see at the output will be equal to 0. So that's why your output resistance is equal to 0 ohms. Now finding out the loop gain, again, you need to find out A times beta, right? And for that, first you need to find out what is beta. So for that, you'll draw the linear equivalent model of the op amp, connect all the resistances that are there in the given circuit, and treat the output of the dependent voltage source as your input, and whatever voltage you get available at the input side of the op amp, that's your output. So you want to find out what is the ratio of the voltage developed at the input of the op amp to the output of the voltage source, the dependent voltage source. And that is true for any feedback circuit. So for feedback, you're taking the voltage from the output, putting it back at the input side. So what is the gain for that feedback? The gain for that feedback is whatever voltage is available at the input side divided by the voltage that was available at the output side. So that's the feedback gain. Feed forward gain is the reverse. Okay, now again, you can solve the voltage divisions that are there, and all of you have already done that in your homework 2 solutions. Questions? Why did we draw a current source VT at the output side? I think this is something that Troy did. So the UPI, or basically the TA who solved this. So I think he showed this to someone that you have a test voltage source over here, and if you have a test voltage source over here, you'll see instead of treating this as your input, you're putting a test voltage source over here and then finding out all the voltage divisions that are happening through the resistances. It is same as treating this dependent voltage source as your test voltage source, right? So it does not matter whether you're treating this as your input or you disconnect that and put another test voltage source and treat that as your input. The gain does not change. The gain is a ratio of voltages at point B over point A, right? So the gain does not change depending on the value of the voltage can be anything. The input voltage can be anything. It could be 1 volt, it could be 1 millivolt, it could be 1000 volts, but the gain will remain same because the gain is just a ratio of the resistances. More questions?
What would you say is the best methodology?
Break the loop. Great question. So it's easier if you just break the loop at the output of the dependent voltage source. So treat that as your input point and find out the voltage divisions happening across the network and find out what is the voltage that is available at the input side. So I find that's the easiest way to analyze the feedback, because you can also break it at any point. Theoretically, you can break it at any point, but then your A and beta, they become very like jumbled up. Let's say you break whichever point you break the loop, one side of that becomes A, the other side of that becomes beta. So theoretically, you can break it at any point and your A and beta will change. But ideally, what do you want? You want your A to remain same so that the calculation becomes easier. That if you know that my A is equal to the feed forward gain. So let me draw something else. Let's say you have markers have gone right. Let's say you have, I'm just drawing black boxes over here to show a feed forward path. So let's say from this point, this is let's say some circuit, and it doesn't matter what kind of circuit it is. It could be an amplifier, it could be a filter, it could be something else. That goes to another block, that goes to another, and then you see that there is a feedback path which may be again context of 2 of these blocks. And then at the input side, you probably add them or subtract them depending on whether it's a positive feedback or a negative feedback. For now, let's just assume that this is a negative feedback. So you have a subtraction over here. Now this is a loop. You can break the loop at any point. Let's say you break the loop here, and your input is coming from this side. If you break the loop here, then only this becomes your feed forward path. Everything else becomes your feedback path. So this becomes your A, and everything else becomes your beta. You can break the loop here. Then this and the first block and the second block together becomes your A. So let's call them A1 and A2, and A1 times A2 becomes your A. And because you have broken the loop at this point, everything else becomes your feedback path. You can break the loop here. So what is happening is that your A and beta, the definition of your A and beta are changing depending on where you break the loop. But if you want to make your calculation simpler, you would want to do it in a systematic way. What's the systematic way? That you already know what is the gain of the op-amp. Let's just treat it as the feed-forward gain. So your A won't change at all. So if you break the loop at the output of the dependent voltage source of the op-amp, so at this point, so this is where you're breaking the loop, which means that your feed-forward gain is exactly equal to A. Whatever is connected after that becomes your feedback gain. So you just need to calculate beta. You don't need to calculate A. A is same as what is given in the question. Right? That's why I would suggest that always break the loop just at the output of the dependent voltage source in the op-amp, which makes your calculation easier. You don't need to calculate A again. You just have to calculate beta, and your loop gain will be beta times whatever gain was provided for the op-amp. But you get this point, right? This is very important. So all of you, just let me know if you get this point, that you can break the loop at any point. What happens is that the definition of your feed forward and the definition of your feedback changes depending on where you break the loop. So if you break the loop at any other point, your feed forward gain will not remain A or the gain of the op-amp anymore. It will be something else. And again, it's more calculation. Why would you do more calculation when you can do it in a simpler way? Question?
So the A with the reference.
Yeah. So it's A times beta. You want your A to be exactly same as the gain of the op-amp itself, the inherent gain of the op-amp. That makes everything so easy, right? That you just need to calculate beta. If you had broken the loop here, then what would be your A? A would be whatever gain you see in the feed-forward path, going through this voltage division and then looking at this one. That will become your A, and the rest of it will become your beta. So you need to calculate both your A and your beta again if you break the loop over here. But if you break the loop at this point, which is the output of the op-amp, the feed-forward gain is just the gain of the op-amp. Right? That's why it's easier. It's the easiest to break the loop at the output of the op-amp itself. So great question.
I know that they use best practice to refer to break the loop at the source.
Yep.
But I know like in some other problems, also broken off or put with resistance to other like points. I guess like how would you start when you put like an RX or RY?
So how do you define those RX and RYs? So that
Where would you start them from?
So wherever you see that there is a network of resistances, it's easier to assume that the equivalent resistance of that complex network is RX or RY. So wherever you encounter something complex, so let me see if we have something complex somewhere over here, or we may need to go back to, I don't know, maybe one of the example problems. But here, I think this is good enough. So for example, for the second problem, as you see, as you're trying to find out beta, again, you break the loop at the output of the dependent voltage source, and you find out what is beta. So now your question is, what is my RX? What is my RY? What are those resistances? So as you look towards right, so your starting point is here, right? Your starting point is this point, right? Just at the output of the op-amp. You look towards right, you see this R0, and then you see a parallel combination of this, whatever R2 or RL, connected in parallel with this R2, this whatever large resistive network. So wherever you see a large resistive network, simplify, call it RY, for example. So you have R0 connected in series with a large resistive network. So let's call it RY. Now think about it, that what voltage are you interested in? Are you interested in the voltage across R0, or are you interested in a part of the voltage across RY? You're definitely interested in part of the voltage across RY because you'll propagate toward this direction and eventually you'll find out what is the voltage here. So you are interested in part of the voltage that you see across the RY resistance. So that's why when you take this first voltage division, that is RY divided by RY plus R0. You're not interested in the voltage across R0. If you had been interested in the voltage across R0, this division ratio would be R0 divided by Ry plus R. But you are interested in what happens in Ry and what happens after that. So that's why you are interested in that part of the voltage division which contains Ry. Okay. So then you propagate again toward the right hand side, you see R2, and then again a large network of resistances connected in parallel with R2. What are you interested in? You are eventually interested in that large network of resistances, which is called Rx. So in this case, the ratio, the voltage division ratio becomes Rx divided by Rx plus R2. And eventually, within Rx, you find out that, okay, there is a parallel resistance R1, and then like in parallel to that, you have Rin plus R3. Now you are interested in, of course, the voltage division between Rin and R3. So that's the third voltage division you have, Rin divided by Rin plus R3. And because you are interested in the voltage across Rin is in the numerator. Yeah. I hope that answers your question.
Yeah, so basically parameters parallel.
Wherever you see something complex happening, simplify it. Okay. All right. So in this way, you can find out what is your T. And of course, if you find out your T, you can find out your closed loop gain, which is basically A infinity divided by 1 plus 1 over T, even though that was not asked in the homework, but you can find out what is your closed loop gain. Now, what is happening to the closed loop frequency or the closed loop bandwidth? That will be your open loop bandwidth multiplied with 1 plus T. That's what we had written in the board initially, right? Your gain reduces by a factor of 1 plus T. Your frequency or the bandwidth increases by a factor of 1 plus T. Because the gain bandwidth product always remains constant. Remember that we had drawn this curve that x-axis is frequency, y-axis is gain. At low frequency, the gain is constant. After the frequency at which you encounter the bandwidth, it will follow at minus 20 dB per decade slope for a first order response. If it is a second order amplifier, that would be minus 40 dB per decade. Those things will come to those things later on, but not right now. Right now, let's assume that this is minus 20 dB per decade. What's the meaning of minus 20 dB per decade is that if you increase the frequency by 10 times, your gain will reduce by 10 times. And that is something that we had proved from the equations as well. That why does, and if you don't remember, please go back to those video lectures to see why, if you increase your frequency by 10 times, your gain will reduce by 10 times. You prove this mathematically. Okay. So what does that mean? At this point, you had a fixed gain. Let's say you had a gain of 100. You increase the frequency by 10 times, you reduce the gain by 10 times. So when you increase the frequency by 10 times, your gain will be 10. You increase your frequency by 100 times, your gain will be equal to 1. So what is the gain bandwidth product? At this point, the gain bandwidth product is, or the product of your gain and frequency is 100 times, let's say, F1. So at this point, it's 100 times F1. At this point, it's 10 times 10 F1, right? Because your frequency became 10 F1 and your gain was 10. So what's the gain bandwidth product? It's still 100 F1. At this point, your frequency is 100 times more, but your gain is 100 times less. So what is the gain bandwidth product? That is still 100 times F1. So the gain bandwidth product remains same at all points in this particular plot. Now in open loop, this is how your gain and the bandwidth will look like. In closed loop, you'll reduce your gain by 1 plus T0 times, or loosely speaking by T0 times. So your bandwidth will increase by T0 times. Strictly speaking, 1 plus T0 times. So that's what you'll see. So because you know what is your T0, you'll know that what would be my increment in the bandwidth. So bandwidth will be increased by 1 plus T0 times. So that would be your closed loop bandwidth. All right. So I think I'll not go over question number 2 because this is very similar to question number 1, and we just want to have some time for homework 3 similar problems as well. Homework 3 problem. Homework 2, question number 3. Here you are asked to find out I0 over IS. So it was a current domain problem. And I think A infinity, most of you have found pretty well. You find out what is your I0, what is your IS, and you just apply the nodal analysis, KCL and KVL to find out that ratio. So just go over this solution. It's nothing special. It's just doing the KCL and KVL in the right way to find out what is your A infinity. R in and R out is again something that you can find out. I'll probably emphasize on how to find out your loop gain, how to find find out your T naught. Okay, so you can do it in a few different ways. Of course, you can assume. So what is your target here? You want to find out what is beta. How much of the output quantity is fed back at the input side? You want to find out that fed back input quantity divided by the output quantity. That gives you the feedback gain beta. Now, to do that, you can use both the approaches related to voltage domain or current domain. You can assume that the op-amp, because it was given in the problem, right? That the voltage gain of the op-amp was maybe 400 or 500. So you know from there that you can consider the output at the output of the op-amp, you have this dependent voltage source. If you have a dependent voltage source, you'll have a series resistance to it, and you can find out what is the feedback path gain, what is beta, assuming that this is the dependent voltage source. You can also do, and in that case, what will be beta? Beta will be the input voltage, the voltage developed across Rin, divided by the voltage available at the output of the dependent voltage source. So your beta will be a voltage over voltage quantity. Okay. You can also find out beta as a voltage over current quantity. So you can model the output of the op-amp as a dependent current source instead of modeling it as a dependent voltage source, and some of you have done it. What would be the differences that if you model it as a dependent current source, let's say I put a current source over here instead of a voltage source. So first thing that will change is basically this R0, which was a series resistance. And some of you have made a little bit of mistake over here that whenever you have connected a current source, you still consider the output resistance as a series resistance. That cannot happen. The current source will have a parallel resistance, which is R0. Because if you don't do this, the Thevenin and Norton equivalence will not be there. You know this from a Thevenin and Norton equivalence that you can represent any voltage source as a voltage source in series with a resistance. That can be considered as an equivalent current source with a resistance in parallel. So if you are considering this as a current source, consider this resistance in parallel, not in series. And then do the same calculations. Say do the similar calculations of voltage division across all these resistances. Eventually you'll find out a voltage at the input side, right? And you can call your feedback factor as the voltage again available at this point divided by, or basically the voltage that gets developed across Rin divided by the voltage available at this point. That gives you your feedback factor. And why I'm doing this is that you can assume any of these cases. You can take it as a voltage controlled voltage source at the output of the op-amp, or voltage controlled current source at the output of the op-amp. Eventually you'll reach the same answer. You can just try it at home, and if you are not able to find it, maybe we can discuss more over emails or during the office hours. But just do it at home. You'll see that you reach the same beta factor or the same beta value, irrespective of whether you consider the voltage source or current source. But if you consider the current source, the resistance will be in parallel, not in series. Questions?
I don't know. That's AP, say AP for
If you consider it as a dependent current source, it will be AI. But yeah, what I did is that I just overwritten on top of what was given earlier, right? So of course, it will not give an AV anymore. It will become AI because you're considering a current source. But good point. All right. So let me know if you have more questions on homework number 2. Again, FCL can be found out as 1 plus T times F1. And you'll see that even though your F1 or the open loop bandwidth is 1 kilohertz, the closed loop bandwidth is about 60 kilohertz. Questions? Could you repeat that again? For the op-amp, yeah, okay, good point. The op-amp's input resistance is still very high. So at the op-amp, so as I said, that the output of the op-amp can be modeled as a voltage controlled voltage source, or a voltage controlled current source, which means that the output you can consider as a voltage or a current, but the input is always voltage. The input of the op-amp is always voltage. There cannot be currents, a large amount of current going into the op-amp. Yeah. So input is always the voltage developed across this resistance. Output, you can model it as GM times that voltage. So to answer your question, so that's transconductance times the input voltage. That's the output current. Or you can model it as AV times V in. That's a voltage controlled voltage source. All right. So let's quickly discuss some of the problems which are very similar to your homework 3. And I have uploaded this document in Canvas as well, so you can go over it and let me know if you have more questions. So here, again, it's the same thing that you needed to find out A infinity and other stuff. For example, R in, R out, A infinity, loop gain. But along with that, you wanted to find out what is the closed loop bandwidth as well, which is something that we already looked at. The only thing that will be asked in terms of closed loop bandwidth is that whether you know that closed loop bandwidth is 1 plus T naught times the open loop bandwidth. Or you can say it's just T naught times the open loop bandwidth, it will be very close, and that's fine. If your gain reduces by T naught times, your bandwidth has to increase by T naught times. That's the crucial part. Okay, so for example, you wanted to find out A infinity, beta, T naught, and FCL for this circuit, as well as maybe for another circuit. And these are very similar to your homework number 2. And I'm hoping that you can solve all these things. But the solution is also provided. So please go over the solution. I wanted to discuss a little bit about, I think, problem number 2. So let me see if I have that. Yeah. So problem number 2, as you see, is a more complex circuit. So whatever you have seen before was just probably 1 or 2 resistances, maybe 3 resistances in total. Here you have a lot more number of resistances and capacitances. And you are asked to find out, or you are asked to basically choose the values of C1, C2, and C3 to set the lower 3 dB frequency to a particular value. Okay. Now, what does this mean? What do you want here? As you see that the capacitance, so you'll see that at the input side, you are seeing a new network right now. So you're seeing something like this. At the output side also, you see something like that. And then there is a capacitance and resistance as well, which is connected over here. So there are 3 different RC networks that you see already connected to the input or output for this circuit, which you have not seen before, right? And why are these capacitances and resistances there? These are presented because of something that we have talked about before, but we haven't talked about it in detail. That is called biasing the op-amp or DC biasing the op-amp. Right? We have said that you wanted to bias the op-amp at a particular DC voltage, and only then you can expect the op-amp to provide AC gain. So the job of this circuit, the RB1 and RB2, which is connected here, as you see, in between VCC, which is 10 volt, and ground, which is 0 volt, you have connected 1 mega ohm and 1 mega ohm, right? Now, since these 2 resistances are equal in value, what would be the DC value at this point, at the midpoint of RB1 and RB2? That would be half of the VCC, right? Pure voltage division. So you'll have 5 volt DC at this point. So that's one way how you can apply a DC bias point at the input of the op-amp. But at the same time, you have to apply the AC as well. So just remember that if you ignore the DC biasing, what we are doing is that we are providing the AC input to the positive input of the op-amp. So you know that this is a non-inverting op-amp configuration. The only difference is that you have a biasing network at the input side. Okay. So how do you combine the AC and the DC? To combine the AC and the DC, you put a capacitor in between, which is called a coupling capacitor. So C1 is basically called a coupling capacitance. Similarly, C3 is a coupling capacitance at the output side. What's the job of a capacitance? What is the impedance of a capacitance? It's 1 upon j omega C, right? 1 upon j omega times C. That's the impedance of any capacitance. So what's the impedance of a capacitor at DC, at zero frequency? Infinite, right? Because if omega is zero, your denominator is zero, so the impedance of the capacitor is infinite. So in terms of DC, the left and right side of the capacitor is decoupled, it's isolated. You have infinite resistance between the left side and the right side in terms of DC. So the DC value on the left side of the capacitance can be different from the DC value on the right side of the capacitance. Question?
So basically, what the capacitor does do is it isolates the signal.
It isolates different parts of the system. So for example, the DC voltage at the left side of the capacitance can be different from the DC voltage on the right side of the capacitance.
Like 5 volts.
Yeah. So this will be 5 volt. That will not be affected by any DC voltage here. So maybe the DC voltage on this side is 0 volt or 1 volt. That does not matter because you have a capacitance in between this. Let's say the DC voltage here was 0 volt and you want to establish a DC voltage of 5 volt over here. If you did not have the capacitance, the AC will still come in. But the problem will be that the DC voltage at the AC source will try to fight with the DC voltage that you are trying to create by doing this resistive division. So there will be a fight between those DC voltages and you don't know which one will win, right? So it would not be 5 volt, it will not be 0 volt, it will be somewhere in between. And that's you make your life very, very hard whenever you're trying to do that. So it's better to isolate, it's better to decouple those two DC voltages, and that you can do by putting a capacitance over here. Okay. People who have worked with audio amplifiers, I think you already know about this stuff, but this could be new to some of you. But this is how you isolate different DC voltages or DC points. Similarly, at the output side, if you put this capacitance, you'll isolate whatever DC voltage you want to develop at the output side versus whatever DC voltage you develop at the output of the op-amp. So again, this capacitor just isolates the DC points or the DC voltages. In terms of AC, you'll just assume that you have the capacitance in a way that what is AC? Let's just assume infinite frequency. If it is infinite frequency, then the denominator is infinitely large. So the impedance is 0. So in terms of AC, the capacitor is a short, provided that your 1/j⍵c is very small. In terms of DC, the capacitance is an open circuit. Okay. So that's all we are doing at using the RC networks at the input side and output side. But now there is just look at this point that this RC circuit, the RC circuit that you see marked over here, that is connected to the positive input of the op-amp. There is another RC circuit eventually connected to the negative input, and another RC circuit connected at the output side. So there are 3 different RC networks over here. If you try to find out an exact solution of this entire network, let's say you are trying to find out the exact voltages at every point, it makes your life very, very hard again. As circuit designers, you would always want to assume certain simplifications. What kind of simplification do we assume generally here? Is that because these RC circuits are connected at 3 different points of the op-amp, one is connected to the positive input, and you already know that the positive input is sort of decoupled from the negative input for the op-amp. There's no relation between the positive and negative, except for the fact that you have the virtual ground property. So generally, this is connected at a different point, this is at a different point, this is at a different point. You'll consider them as isolated RC networks. And the other thing that is important is that you have this RC circuit at the input side. What is the RC circuit doing? It's doing some kind of filtering as well, because any RC network will do filtering. And we learned in class that if you have a resistance in series and then a capacitance in parallel to ground, this forms a low-pass filter. Here it's the opposite. You have a capacitance in series and a resistance to ground. So it forms a high-pass filter. I'll not go through the equations because there's not much time, and I just want to talk about the important things. You can do the calculations and figure out why it is a high-pass filter and not a low-pass filter. But you can already guess intuitively that if this is my low-pass filter, R in parallel with C, and this is something we solved in class, solve this in the same way, you'll see that C in parallel with R, that will be a high-pass filter because that's just the dual of it, right? It's just the dual network, the dual RC network of what we have seen in class. So R is replaced by a C is replaced by a R. So of course the LPF response, low pass response will be replaced by a high pass response. So that's why in this case, you will have a high pass response as well, along with the low pass behavior of the op amp. So your gain, instead of looking like this, which is a low pass response, the gain will eventually look like a band pass response. So it will have a high pass cutoff, a low frequency high pass cutoff, and a high frequency cutoff for the low pass filter. So it would look like a band pass filter, and you can calculate these RC values in isolation. The solution is provided here. Please go over the solution. If you do not understand the solution, you can discuss with me. You can discuss with the APIs or TAs. Their office hour is also there tomorrow. I think Troy has his office hour tomorrow. So please consult with him on how to solve this problem. This is not exactly same as the homework 3 problem, but just the numbers are different. Okay. So please go over the solution, try to understand it. If you do not understand, please talk to Troy. And this will help you in solving the homework 3 problems. Okay.